inshallah, short lecture. Before we start, I'd like to mention that, inshallah, on Friday, 10 p.m., have a quiz using OER. Same way like the midterm exam, but it will be short exam, only 10 or 15 minutes only. So on Friday, this is Friday, means tomorrow, 10 p.m., you have a quiz. The content of the quiz will be graph theory and also cryptology until the end of this lecture, until the end of today's lecture, what subjects we will cover. It's included in the quiz. Yes, tomorrow at 10 p.m. inshallah. Your quiz will be tomorrow at 10 p.m. using OIS system, same way like the final as a midterm exam. Okay, so to start our lecture today, I think even we will, yes, we start at 10 and we will finish early also. So, in cryptology, we have 3 lecture notes. Okay, we already give this one with 10 and 11, which speak about some terminologies, speak about simple ciphers with examples we give. Also, we start to speak about cryptography or cryptographic algorithms. And we mentioned that we have 2 types, symmetric and asymmetric. Symmetric, we have 1 key for encryption and decryption. Asymmetric, we have 2 keys, public key for encryption, private key for decryption. And then we take the example RSA algorithm for encryption and decryption. And we saw how to generate public and private key of this algorithm and how to use it. Then we mentioned the digital certificate and the digital signature and how it's work. Then second lecture note is cryptography. I think we still did not finish it yet. So in this lecture note, we already mentioned the basic cipher techniques and we give some examples in how it's work. Yes. So we mentioned this techniques, each technique and how it's work, and we stopped, I think, here. This last subject, we already take it binary cipher and take example how it's work. Okay. So we have another example for cryptology or cryptographic algorithm here, or way for encrypt and decrypt messages. Because when we speak about messages, anything transfer in the network or internet, we call it message. Because anything, video, document, anything will be divided into packets. These packets, we call it a message. Okay, between the sender and receiver. Okay, so as we mentioned last time that there's no unbreakable cryptographic algorithm, but the scientists said that one-time path, OTP, it's one of the unbreakable encryption algorithm. And we will mention why it's unbreakable and we will give examples for it. So we will speak about OTP and how it's work, one-time path, or have three names, or random cipher or perfect cipher. Perfect cipher because they think that it's a perfect way. Then why we don't use it always, we will see why. Okay, what's the idea behind it? First of all, the message will be represented as a binary string. So any message, any document, video, extra, blah, blah, will be converted into a binary string set of or sequence of zeros and ones. Okay. Of course, it's easy to convert any message to 0 and 1. You can use the ASCII code to convert the character of any message to numbers, then numbers to zeros or and ones. Okay, so this first point, the message will be presented as binary string. The key, it's a random sequence, random. From here comes the strength of and the power of this way of encrypting. It's a random sequence of zeros and one that have same length as the message. So if the message 100 bit, the key will be also 100 bit. Okay, same length as the message. The key will be same length as a message and will be random generated. Okay, but because any algorithm, when we generate the key, we need two things here in the key: to be random, which make power for it, and to be balanced. The balance here important also. What's the meaning of balance? We need the number of zeros and one in the key to be same. So if we have, for example, 10-bit string or 10-bit binary string, we need the key to be 10 also bit, but 5 of this 10 zeros, 5 will be ones, but randomly appear. Okay. So to make balance between zeros and one. So how's the encryption done? Okay. We have the message as zeros and one. We have the key as a random sequence of zeros and one. We will encrypt the message by add the key to the message using module 2, or shortly use the operation, binary operation exclusive OR. XOR, yes, you know XOR. Usually we use this symbol for it, XOR. We already mentioned it before, okay? XOR or exclusive OR will be used to merge the key with the message. So the key and the message will be merged using XOR to get the ciphertext or encrypted text. Okay, so just fast review for the XOR or exclusive OR. If we have 2-bit strings and we will do exclusive OR, if we take each 2 bits, so if the 2 bits same, 0 with 0, the result 0. 1 with 1, the result 0. So if they are same, the result 0. If the 2 input different, the result will be 1. So 0 with 1, the result 1, because they are different. 1 with 0, the result 1. So this is the exclusive OR. Okay, so here example for one-time bad or OTP algorithm. We have message IF or F. So first, this message will be converted into byte string. So we have this byte string. This I, this one F. Then we will go to generate a key. So this is the message or the plain text. The plain text. Here's a key. How to get the key? It's random. Okay, so the key random generated. But look to number of zeros and one. We have 1, 2, 3, 4, 5, 6, 7 ones. 7 ones. And how many zero? 1, 2, 3, 4, 5, 6, 7 zeros. Why? Because we need balance between number of zeros and one in the key. This balance makes the key more perfect. Okay, so now we have the plain text. For the plain text, we have the key. What we will do, XOR, exclusive OR, to get what? To get the ciphertext, the encrypted text. So make XOR. If they are same, the result 0. If they are different, the result 1. So 1 with 1, 0. 0 with 0, 0. Same, 0. Different, 0, 1, 1. 1, 1, 1, because they different. 0 with 0, the result 0. 1, 1, here, different, so 1. So this is the ciphertext after we make XOR operation. Now, how to decrypt the message? Same idea. You have ciphertext, XOR the key. So, which key? Same key. Same key. So, we make XOR to get the plain text again, or plain text. So the 0, 1, different 1, same 0, same 0, different 1, and so on. So the plain text is the original message. Like this, we decrypt it. I want to ask you, what's the type of this algorithm? Is it symmetric or symmetric? And why? So OTP, Is it symmetric or asymmetric? By the way, when I present the lecture and I speak, if you have a question, you can open the mic and ask your question. When I ask you if you want to answer by writing, okay. If you want to open your mic and answer, also it will be okay. Yes? What's the type of OTP? From this description, is it symmetric or asymmetric? Hello. How many ones you? How many one here online? Okay. Do you know what's the difference between symmetric and asymmetric? We mentioned it, and I mentioned it just now when I make a review for the previous lecture. What's the difference between symmetric encryption algorithm and asymmetric encryption algorithm? Any encryption algorithm depends on the key. No, symmetric has only private key, not public key. Have only one key. This key cannot be public. If it's public, it will not be good for encrypt and decrypt the message. Symmetric have only one key. Okay, and this key is shared between partners, between colleagues, between corporate peoples and company, between them. So we have one key only for encrypt and decrypt the message. Asymmetric, we have two keys. One key for encrypt the message and it will be public, and one key for decrypt the message and it's a private key. So if we know that, then look here, OTP, we use same key for encrypt and decrypt the message. So how many key we have? One key, same key for encrypt and decrypt the message. Therefore, this one, OTP, it's symmetric encryption, not asymmetric. And what's the problem with symmetric encryption? What's the problem? Why we cannot use symmetric encryption always? We said that OTP it's unbreakable and yes, it's good for encryption, decryption of the message, but we cannot use it always because it's symmetric. Why we cannot use symmetric encryption always? Because symmetric encryption have one key. So company cannot give the private key for customers, for example. So it cannot be used generally. It can be used between partners. It can be used between colleagues in the same company. It can be used between people that have same concern, working on same data, so they can have the key. But as a company or through the internet or something like this, you cannot give your private key publicly for everyone because anyone have the key can decrypt the message. So what's the important for encrypt and decrypt in this case? Okay, that's the issue. So OTP, it's symmetric encryption, cannot be used widely because most the times we need to hide the private key, and symmetric cannot give us this option. Okay, that's why most of the communication now in the internet use asymmetric key encryption. Why? Because company X or person X can give his public key for anyone. Anyone with this public key can encrypt the message, but cannot decrypt this message and get the information. Okay, so why OTP is probably secure? The security here for OTP algorithm depend on the random key. Because we have random key, every time we generate a random key. So no one knows this key except the sender and the receiver. So sender and receiver have the same key. Use the key for encrypt and decrypt. Anyone here in the middle can get the message. He cannot decrypt the message because he don't have this key. Okay, but if we repeat using same key, it could be broken and could be someone could get the key. But we generate a random key. The random key every time make it very hard to guess what's the key, because if you use, for example, brute force way, what's a brute force? Means try all the possibilities for the key. Okay, if it's long, then this need very long time, maybe years to break this key, if it's long enough. Okay, another way, it's when you have message and another message and another message and so on, they try to compare the messages to get the key. But if every time you use different key, random key, there is no benefit to compare first message and second and third and so on to get the key. Because even if you get the key this time, next time there's another key, different key, and so on. So here we have two properties that we seek in OTP. First, unpredictable. Why? Because it's random. Second, balance. We have equal distribution of zeros and one. So we have balance key. These are two issues here. Okay, so let's take this example. If we have, for example, okay, if we have this string with 5 symbols or 5 letters, so we need to encrypt it and send it. So 5 letters, then the key will have also 5 letters, yes, to encrypt the message. So to break the ciphertext using brute force algorithm, we mentioned it before that, brute force. What's the meaning of brute force? Brute force, when we mention it with any algorithm, means try all the possibilities. This is the meaning of brute force, means try all the possibilities all the combinations, the possible combination. So to try all the possible combination for the key with the string that have 5 letters, each letter you have 26 possibility. 5 letter means 25 multiplied by 25 multiplied by 25. 5 times means 26 for 5. So you need around 12, 11 something means around 12 million possibilities to make the brute force algorithm. Usually, the messages, it's not 5 alphabet or something like this. Usually, it's long message. Any letter you will add here, it will increase exponentially. 6 letter, 26 to power 6. 7 letter, 26 to power 7. Growing exponentially means you start to speak about billions, trillions, and so on. So message with 20 or 10 letters, it's almost impossible computationally to make or to use brute force algorithm to break it. It's almost impossible. Okay, we return again to RSA algorithm. We already mentioned it before and take example. We will take another example today for it. What RSA algorithm? Actually, RSA algorithm have 2 algorithms. One algorithm to generate the keys. So the generation algorithm, which is generate the public key and the private key, or the encryption key and decryption key. And RSA function evaluation, this is the part that will encrypt and decrypt the message using the key generated. So the key generation part from it, it's the most complex part from RSA. The problem with RSA, if you have not short key, because the key it's depend on 2 prime numbers that we select, which is P and Q. If you have short P and Q, means the algorithm or the key will be easy to reveal and to break. So easy to break it. Okay, the steps we already mentioned last time. Actually, I prefer that way that we already mentioned last time. Okay, because it's I think much easier for you to read it and to memorize it. This one. Okay, this way of writing it, writing the key generation algorithm, it's much easier. Okay, this is a formal way, this one here, the formal steps, which is first choose or generate large prime number or 2 large prime number P and Q. And large here very important. How much large? The numbers should be very large. For example, 512 digits, or at least, or it will be better if it's 1024 digits, as mentioned by one of the scientists, Robin Miller. He mentioned that for the key to be more safe, it's better to use 1024 digits for the prime number, the two large prime number. Okay, after that we calculate n using n equal p multiplied by q. We call this step modulus calculation. Modulus means here the multiplication between p and q. Then we calculate the f, yes, pi or f. This one, pi. In the algorithm, before that, we mentioned it as f, yes? So this one. F or pi, it's same, yes? So pi will be calculated as p minus 1 multiplied by q minus 1. Then we generate the public key and the private key. How to generate the public key? Or we call it the encryption key, E. If you remember, we generate E. E will be a number between 1 and n. And this E should not have common divisor with pi, with f. Okay? So the public key will be combination between E and N. How to calculate N? E actually it's a prime number. So usually we take E as a prime number because we need E to be between 1 and N, less than N, more than 1, and not having common divisor with F. So it will be always a prime number. Private key, here they mention why we generate a private key like this and the relation between E and D, or E and D. So shortly, it's like this. E multiplied by D equal 1 mod pi. You can take this one to the other place. So we speak about E multiplied by D mod n should have divisor by 1. Set here. Here we said E divided by F, the remainder should be 1. Okay, so this one, let me write it again. So we have E multiplied by D divided by pi n or F, okay, should have or should give us remainder 1. Okay, so this one, same examples that we take before. We compute or we choose P and Q. We will take another example now, but this same calculation that I gave before 2 lectures. We choose P and Q, for example, P here 3 as a prime number, and it must be large prime number, but we choose short here to make the calculation simple. So choose P and Q, then we compute N, which is P multiplied by Q, so it's 33. Then we compute yn or f, which is p minus 1 multiplied by q minus 1. So 2 multiplied by 10, it's equal 20. Then we get or choose E or encrypt the message. E must be between, as I mentioned, between pi n and 1, or between n and 1. Okay. And E and F here, n, okay, are co-prime, or shortly, the remainder will be 1. When we make E or co-prime means they don't have a common divisor. Okay, so if we have here Qn as 20 and E must be less than 33, so we have some choices that do not have common divisor with 20. You know the common divisor of 20, we mentioned it last time, which is 2 and 4 and 5, 10, and of course 20 itself. Okay, so we need a prime number that less than 33 and do not have common divisor with this. So we could choose E as 3. We could choose it as K5, cannot, because it's have divisor here. Could choose it as 7, as 11, and so on. We choose it here as 7. So we select, we choose E. So if we speak about large prime number, we have many choices or more choices, which make it too complicated to break this algorithm if we have a large prime number. Then we get D from this relation. Okay, we said D multiplied by E. The remainder, when we divide by F or by pi, it must equal 1. So we have many solutions. One of the solution is D equal 3. Okay, because D equal 7, 3, because E we already select as 7. So 3 multiplied by 7, 21, mod 20, so it's equal 1. This is one possible solution. Okay. So the public key is a combination between E and N. E, which is 7, N 33, and the private key, which is D and N. So D is 3 and N is 33. So we use public key to encrypt the message. For example, here, if we have message 2, so we encrypt it like this. The ciphertext, it's equal the message power E, the encryption, yes, mod N. So the ciphertext equal the message here 2 power E, which is 7, mod 33. If you calculate this, you will find that it's 29. Today, I will mention how to calculate easily the mod without calculator. Okay, this is about ciphertext, how to encrypt the message. To get the message, the original message, or the plain text, M, the message, it's C, okay, the ciphertext, power D, mod N. So C, it's 29 as we calculate here, the encrypted text. Power D, which is 3 here. Mod 33, which is the value of N, then you will get 2, which is the original message. Okay, here another example. We always use the name Alice and Bob, and Alice need to send message for Bob, so she encrypts the message. Here, we choose another two prime numbers, which is 11 and 13. So L equal P multiplied by Q, which is 143, and 5 or N P minus 1 multiplied by Q minus 1, so 10 multiplied by 12, which is 120. Now we need to choose the E, which is less than 120, less than F, okay, and do not have common divisor with 120, and it's a prime number, okay. So we choose here E as 7 because it do not have any common divisor with 120, and it's less than 120. Okay, so we need to generate now D. We said how to generate D. D multiplied by E mod U or pi n, it's equal 1. Yes, so D multiplied by E mod un, it's equal 1. We have, of course, many possibilities. Here, one of the possibilities that D could equal 103, and D must be chosen as a prime number. Okay. So now we have the public key, which is combination between E and N. So the public key is combination between E and N. So it's 7, which is the value of E, and 143, the value of N. The private key, which is combination between D and N. So it's 103 and 143. Okay, so for Bob to encrypt a message and send it for Alice, he need what? He needs this one, the public key, the combination between E and M, and he can calculate the message or the ciphertext M or E mod N. If he want to send message only 9, for example, 9, number 9, as a message, so message which is 9, or E which is here 7, okay, mod 143, so this is the encrypted message. So the original message is 9, the encrypted message is 48. Okay, so C means cipher, yes, text. M means message. So when Alice receives a message from Bob, she decrypts the message using the private key, which is combination between D and N. So how to decrypt the message, as we mentioned before. The ciphertext C bar D mod N. So ciphertext, which is 48, bar 103, which is the D mod 143, so it's equal 9. So this is the original message. Okay, so let's move to the next lecture. No. This one. This one, let's change it as week 13. Actually, we will take it. We will take part today, just short part from it, and the other part we will take it on week or in week 13 next week. So in this lecture, we will mention or we will take another public key encryption algorithm, which is Al-Jamal, and it's more secure than RSA. We will see why it's more secure. Also, okay, let me ask you a question before I mention what's the second subject. When you have symmetric encryption, okay, symmetric encryption means same key will be used to encrypt and decrypt the message. What's the most important issue here in symmetric encryption? You can open your mic and answer instead of writing only. Or you can write, it's up to you. What's the main concern? Let's see, not main problem, main concern when you speak about symmetric key encryption. Okay. What will make the problem for the encryption? If someone can get the key, yes? Because if someone, except the sender and receiver, can get the key, he can decrypt the message and read it, yes? Okay. If I am here in Turkey, in Safranbolu, or in Karabu, and I have partner in USA, for example, and I want to share my key with my partner so we can send and receive encrypted messages using symmetric encryption. What's the main concern here? We need to exchange the key. I need to send the key for my partner, yes? How to send the key? It's a sequence of numbers, this key. So usually we send it using the internet, yes? But how to show that this key protected? How to generate a common key between partner X and partner Y in different places? How they can exchange or share the key? This is the main concern. If you send the key using the internet, it's not secure, yes? How to show that it will be secure to exchange this key? This algorithm suggests a way. So, Diffie-Hellman key exchange its algorithm to exchange the key securely between the partners. Okay, so we speak with about symmetric key encryption and how to exchange the key between sender and receiver, between partner, between X and Y, share the same key, so they have to change this key if or to generate it commonly. Okay, so this is the issue solved by this Diffie-Hellman key generation algorithm. Also, we will speak about hash function. Usually, we need to generate keys and generate a sequence of numbers. So hash functions functions that generate this type, okay, of numbers. So we'll speak about hash functions. So this three parts remain in the cryptology. Okay, so we will start. Today we will speak about part from Al-Jamal public key encryption, or we will speak about it. Then next lecture we will take the examples for it. Okay, so Al-Jamal, it's a public key encryption. So what's the meaning of public key encryption? Public key means it's symmetric. Why it's named public key, not asymmetric? Because its name is symmetric or public key encryption because we use public and the private key. But symmetric key encryption have only one key, which is private key. Asymmetric have public key. That's why sometimes we call it public key encryption. So we take another public key encryption before that, which is RSA. So now we have RSA and we have Al-Jamal algorithm. So it's alternative for RSA. What's the difference? Okay. For RSA, the security of RSA algorithm, the power of RSA algorithm depend on what? Depend on difficulty to get or factoring large integer number, which is P and Q. But if someone can get P and Q, then he can decrypt the message. The Jamal algorithm, it's depend on difficulty of computation, okay? So it's depend on something called discrete logarithm, okay? You know the logarithm with large prime modulus. Shortly, the security of Jamal algorithm depend on having a random key, okay, and have different key every time or different ciphertext every time for the same text. Okay, so one of the advantage for Al-Jamal, same plain text give different ciphertext. Because I will show you that it's depend on some random number to get the ciphertext to encrypt the message. So this random every time change, which is make it very difficult to break the encryption, which make it more advanced and more stronger than RSA. Because here in RSA, you will use same key always. Here, okay, even if you use same key, there is a random number that will be used to decrypt the message. I will show you what I mean. So this means same plain text usually have different cipher text. So same message will be get every time you encrypt same message, you will have different encrypted message. So it's make it very difficult to broke it. Okay. As you can see, all the calculation using the mode K, mode A, mode B, mode K. So before we continue, let's speak about how to calculate the mode without calculation. Okay. Let me just I will open here and we will speak about how to calculate them. Okay, let's take uh, this example. We need to calculate 7 power 6 mod 11 without using the calculator. You know how to calculate it? Try to calculate it without calculator. 7 power 6 mod 11. Okay, try to calculate it. We can take a short break, 10 minutes, until you try to calculate it. Okay, see you after 10 minutes. Okay, so how many of you get it without calculator? 7 or 6 mod 11 without calculator. Anyone calculated? It's difficult, yes. Because 7 power 6 is a very large number. So how to calculate it without calculator? Okay, let me show you. Actually, when we have power or multiplication, you have to know that the mod, it's like the division, can be divided into any part of this power. So this one, we can write it like this to make it more simple. 7 power 6, we can write it 7 power 2 all power 3 11. So 7 power 6, we write it as 7 power 2 power 3. Same, yes? This means 7 power 6. Okay, 7 power 2, I think it's easy to calculate it. It's 49. 7 multiplied by 7, 49. Power 3 mod 11. Because we can always distribute the mod and use it many times if we have multiplication and power and so on. So we will take this one inside alone, mod 11. So if we said 49 mod 11, it's easy. What's the meaning 49 mod 11? Means if we divide 49 by 11, we take the remainder. Okay, so what's the remainder when we divide 49 by 11? So the remainder is how much, you know? 5. Because the nearest number is 44, which is 11 multiplied by 4. So what's the remainder is 5 to have 49. So this one, 49, becomes 5 power 3. And we will have always mod the mod until we get this ratio. Always you can make the mod until you get number less than 11. So until you get answer less than 11. Because the mod on 11 always less than 11. Yes. So now we have 5 power 3 mod 11. It's become easy. Yes. 5 power 3. It's 125. 5 multiplied by 5 multiplied by 5. 5 multiplied by 5, 25. Multiplied by 5, 125. Okay, so 125 mod 11. How much? It's easy also to calculate it. The most close one, it's 11 multiplied by 11, which is 121. Yes? So what the remainder here, when we divide by 11, 4. So 125 mod 11, the result is 4. So when we said 7 power 6 mod 11, the result is 4. How to get this 4 without calculator? As you can see here, we just can distribute the mod on the power or multiplication. So we can simplify this power to make it something for another thing. Then we make the calculation easy. Okay. Another issue in the mod. Here, when we speak about power, yes. What if we have number with minus power? For example, 4 power minus 12 mod 11. Okay, who can calculate this one without calculator? You know how to calculate it without calculator? 4 power minus 12 mod 11. Just raise your hand if you know how to calculate it without calculator. Okay, so no one, but I will tell you. I will make it easy for you. Okay, no. We have here like a rule to do it. Consider this one P, and this one without the minus, okay, K, and the number X. So the rule says this one, when we have mod, it's equivalent to take same number, which is X here. We name it X to make it general relation or general rule. So the number itself, X, power 1, power P minus 1 minus K. So now replace this rule here. So P means here, the mod. K means the power, this one here, but without the minus. And X is the number. Yes. So I will write this rule here. So this one become X, which is the number 4, for P, which is 11, minus 1, minus K, which is 12 here. Of course, don't forget the mod. Always we have the mod. When you have multiplication or power, the mod will not finish it until you have number less than this number of the mod. So if you still have number more than the mod number here, you still have to do the mod operation. So you can apply the mod operation as many times as you want, or as needed, not as you want, until you get number less than the right hand side of the mod. So this one, it's 4 power 10 minus 12. So it's 4 power minus 2 mod 11. Okay, but we still have minus. Okay, don't worry. If you still have minus, apply it again. We can apply same rule, this rule, many times. Okay, so 4 minus P, which is still 11 here, power p minus 1 minus k. Here k become 2, yes? So minus 2 mod 11. So it's 4 power 8 mod 11. So this one, 4 power minus 12 mod 11, it's equivalent to this one, which is 4 power 8 mod 11. I think it's easy to calculate 4 power 8 mod 11 same way as what we did here. So let's calculate it. 4 power 8 mod 11, we can write it as 4 power 2 power 4, because 2 multiplied by 4, it's 8, yes? So power 8, we can write it as power 2 power 4 mod 11. So this 16 power 4 mod 11. So now we can take the mod for the 16 inside here. 16 mod 11, it's 5. The reminder, when we divide 16 on 11, it's 5. So 5. Now this power 4, I will write it as power 2 power 2 mod 11. So 5 power 2, it's 25. And always we have mod 11. Or always we have the mod 11 or mod 7 or mod anything. Here in this example, mod 11. So 25 mod 11, how much? It's a 3. 3 power 2 mod 11. From where this power 2? This is outside power, yes? And here 25 mod 11 becomes 3. So this 9. So 3 power 2, it's 9. Mod 11, it's 9. So this is the result. It's 9. So 4 power minus 12 mod 11, it's easy to calculate it, and it's become 9. Of course, as you can see here, there is many steps, but I can make it shortly if I use it many times, then I can directly write this one like this. Okay, this one means 4 11 minus 1, so it's 10 minus 12, so it's power 2 minus, of course, mod 11. Then I can make it also another time, and shortly I can say 10 minus 2, so it's for a mod 11, and so on. Then you can complete. So this is a way of calculate the mod without even use calculator. You don't need calculator actually to calculate the mod. Okay, what if I have a huge number like this, 2, 3, 4, 2, and so on, mod something. Mod 11, for example. This multiplication, you can write it as number multiplied by another number. Then take the mod for this number and take the mod for this number, multiply the result, and take the mod of the result. This one way. Another way, you can use the minus for, so for example, 40 48 mod 11. Okay, I give short one just to show you. So you can every time minus 11. Okay, until you get number less than 11. So minus 11, 39. Yes, minus 39. Okay, 37. Sorry. Okay. Minus 11, 26, minus 11, 15, minus 11, 4. So we get number less than 11. So this is the result of the mod. Of course, when you have large mod number here and large number, it's much easy to make the minus here or divide this number into two numbers multiplied by each other. Or make it as a power if you know what it's about. Okay, like this calculation for the mod. Of course, it's have relation with the encryption using the mod. Okay, so let's return to our subject, which is Al-Jamal encryption, public key encryption. So how to do the encryption? Imagine that Alice wants to generate her keys. So she will generate public key and private key. Now the power of German encryption not only about the strength or power of the keys, also because when we encrypt the message, we use random generated number also. Okay, I will show you what we mean by example. Okay, first of all, first step is to choose a large prime number. Always we speak about the prime number. Large prime number, we call it P. Okay, ignore this A. This A means Alice. Okay, means this P, the large prime number of Alice. Okay, so generally we speak about large prime number P. Okay, this large prime number usually at least 200 or 300 digits. So when you speak about 200 digits, means you have one with 200 zero in the front of it or something like this. So it's billion of digits. So it's a large or huge number. Okay. Also, Alice will suggest a number called alpha. This alpha, it's module from P, so it's generated from P. Okay, it's let's say it's multiplication from P. Okay. Of course, we will take it by examples. All this, how to calculate it. Also, she will generate a random integer value, which is D. D is the private key. So the private key, it's random generated, and it's between 2. Why between 2? Or could be equal to until P minus 2. P, it's a large prime number. So it's between 2 and, because we don't want it to become 1, yes? So it's between 2 and the large prime number p minus 2. How many possibilities we have? Too many possibilities to get this private key. So if you use a brute force algorithm, means try all the possibilities, you need years, okay, to get this private number. So now, so the private key, or for decrypt the message, this number or this integer, it's a huge integer between 2, okay, 2. Usually we take it a random, so could be 1 trillion, 1 billion, we don't know how much, and p minus 2. Then Alice computes beta. So we have alpha, it's suggested as a module for p, and we calculate beta. How to calculate beta? Beta, it's equal alpha or d. So we use this private key to generate beta. So alpha power d mod p. What is p? A large prime number. So the public key now, after we calculate p, beta, and we generate alpha, and we select a large prime number. The public key is a combination between p, alpha, and beta. So anyone know p, alpha, and beta. And the private key, this one's the public key. The private key is D. No one knows D except Alice. Okay. This one part from the security that no one knows this private key except Alice. So in this term, it's like RSA, but which make or give more power for a Jebel algorithm. It's the way of encrypting the message. Because the way of encrypting the message or every time give us different message. Why? I will show you why. Let's say that Bob want to send message for Alice, so want to encrypt message M and send it to Alice. First of all, the message must be shorter than P. Bob no P, yes. Bob no P, no alpha, and no beta. Because this is the public key for Alice. So Alice can distribute this public key for anyone. So when I said Bob or Alice, not Bob himself, not Alice herself, means the algorithm on the computer at Bob's side or Alice's side. So the message sent by Bob must be less than or shorter than P. Shorter, not less, shorter. Okay, what if this message larger than P? You can divide it into M1 and M2. Same the idea of sending message in the internet or network. The message will be divided into packets because we have specific size for the packets in the communication. Same the idea. If the message larger than P, it will be divided into parts, each one less than P. So if it's still larger, also you can divide it into more parts. Okay, so here's the second strength for this algorithm. For Bob to decrypt the algorithm, he will choose a random integer, k. And this random integer, it's secret. Even Alice don't know this k random integer. Here, but how Alice will encrypt the message, decrypt the message, because Bob encrypt the message using a random integer k, and Alice don't know this k. I will show you how Alice will decrypt the message without even knowing this random integer. So because this random integer k, it's not shared from Bob with anyone, so anyone in the middle gets the message, cannot decrypt it, except Alice, because it's depend also the decryption will depend on the private key of Alice. I will show you how. Okay, so after Bob select a random integer k, any random integer k, okay, Bob will compute the decrypt or decrypt the message computing two things, R and T. So the ciphertext, it have two parts. The encrypted message have two parts, R and T. Okay, R and T. How to calculate R? R, it's alpha power k. What k? Random integer generated by Bob. No one know it, even Alice. Okay, so R will be calculated as alpha power k mod p. And T, because we need to calculate R and T. We calculate R like this. T, it's beta power k multiplied by the message mod p. Then discard k. What's the meaning of discard k? K will be removed from Bob computer. Just will be used for calculation one time and discard. Next time he will send even the same message, he will generate another random integer k. That's why same message, if you send it more than one time, every time will generate different encrypted text. Okay, so Bob will send the encrypted message, which is combination between R and T, to Alice. Now Alice's work is to decrypt R and T. But you will say, but Alice don't know K. Let's see how Alice can decrypt this message R and T. When Alice receives the encrypted message R and T, she will decrypt the message using this computation. TR means T multiplied by R power minus D. Okay, let's see. What T? It's this one calculated by 4. What R? This one calculated by 4. What D? It's the private key of Alice. Anyone know D? No one except Alice. Okay, so you sure this one will give us M, which is the original message? Let's see if this one give us M. Because what's the meaning of decrypt the message? Get the original message, get M. So let's see this one, what its original. Okay, TR power minus T. Let's see what T. T here. Just this T. Okay, so T, it's equivalent to beta power K M. So this is T, beta power Km. But Alice don't know K, yes? But she know T and R. Then it will give us the message. Let's see if this one give us the message or not. The other part, which is R, yes? This R. R, it's alpha power K. What about this mode and this mode? We said if you have mode and multiplication, you can take it outside as a general. For all everything, you can use this mode. So this is the mode. This one and this mode, mode P, we take it on the side here because it's general, yes? Okay, so what we have, alpha power K. So alpha power K, it's R. Power what? Power minus D, we said, yes? Power minus D, so power minus D. Okay, you remember how we calculate beta? How Alice calculate beta? Return here. This is the way of calculating beta. Beta equal alpha power D. Mod P, of course, okay? So beta it's alpha power D. So if we remove beta, we put alpha power D. So instead of beta, put alpha power D, and we still have power K multiplied by M, this one, and this one as it. Okay, look to this part and this part. This one, alpha power dk, and this one, alpha power minus dk. Okay, when you have 10x multiplied by 10 power 5 multiplied by 10 power minus 5. What's this? 10 power 5 will go with 10 minus power 5. So what remains with us? X. Same idea here. Alpha power dk with alpha power minus dk, because minus means it will go to the division. So if this one divided by this one will gone. What remains with us? The message. So the remain what? The message itself. So without Alice knowing the key or the integer, random integer number k, she can decrypt the message, which is t power r minus t multiplied by r minus power d. Okay, so this is a calculation. Okay, so let's speak about some issues here about the security. So if always in our examples, if is a hacker who tried to get or decrypt the ciphertext. So we said the communication between Alice and Bob. So Bob decrypts the message and send it for Alice. Imagine that Eve in the middle gets this message from the communication channel and try from the internet, from the network, and try to decrypt it. So she gets the ciphertext R and T. But if do not know D, which is a private key. So if cannot calculate D. But we know that beta is this one. And in this case, D will be some logarithm of alpha, like this. So we call it discrete log here. So she can get D if can find D if she can compute this discrete log with a very large prime modulus that computationally it's extremely difficult and cannot be calculated easily. Need years to calculate it. So another issue that makes this encryption strong, that every time Bob means a person who will decrypt and send a message, every time should use different integer, random integer k, which makes the proof for this algorithm is extremely difficult. Okay, next time we will take examples for this algorithm. This is a calculation, yes. And then we will speak about Diffie-Hellman key change algorithm, how to change the key, okay? And then we will speak about the hash function, okay, to generate the numbers. Okay, that's all for today. So if you have any question here, we already finished. Okay, so again, you have tomorrow, inshallah, 10 p.m. You have a quiz using OIS system. Don't come after next day and said I forget or I have connection problem or all this excuse not acceptable. Find a good internet. In any exam, it will not be accepted, this excuse. Find good internet and good place and answer the quiz. It's short quiz, around 10 to 15 minutes. 10 to 15 minutes, something like this. Okay, and always try to solve your exams, online exams, using laptop or computer, not using your mobile. Okay, so see you. Salam alaikum. That's all.